Yesterday you were introduced to the idea of parametric equations. And parametric equations are actually really powerful. Up until now, we've had particle motion problems where our particle is only allowed to move in a straight line, and it can move forwards and backwards, but it's only going to move in a straight line because we have either x or y changing with respect to time. Parametrics are going to allow us to have a x-coordinate and a y-coordinate that change with time. So we wind up having particles that can travel in the plane, and they can take weird and different paths as they're traveling in the plane. And we can still talk about their velocity and their acceleration, but they're moving in two dimensions instead of just one. So because they're curves and because we can graph them and we can take a look at their shape, they definitely have a slope. We can draw a tangent line. And so we talked about the slope formula for parametric curves yesterday because we have to do the chain rule in order to get the slope, so we wind up having to do division to get that slope. The same thing is true when we take a second derivative, but parametric curves obviously have concavity because we can talk about concave down like a frown and up like a cup for these kinds of curves. You don't have to memorize this or write it down, but I want to emphasize that when we take the first derivative, we have a function of t here. We don't have a function of x, we have a function of t. So our first derivative is actually a function of f. So when we take a second derivative with respect to x of this thing, so we can get a second derivative, when we take a derivative of this part with respect to x, we have to do the chain rule. So we're going to take the derivative of f but then we're going to treat t like it's a function of x. So we're going to have dt dx because we took a derivative with respect to x. But that's weird because we don't like seeing dt dx. So the way we actually write it is we say, okay, we're going to take a second derivative and then divide by dx dt because we're used to seeing dx dt and not dt dx because that's weird. So that's how we find second derivatives. And really, I just wanted to show you that. You don't have to memorize it because I wanted you to know that second derivatives feel like they should be more straightforward than they are. It feels like you should just take a second derivative, but because it's with respect to t, because of the chain rule, we wind up having to divide by dx dt again. I'll show you how to use this second derivative formula, and that's what you need to be able to do. So first, we're going to find dy dx, just like we did yesterday. So dy dx dt would be negative 2t, and dx dt would be 3t squared minus 1. So dy dx would be negative 2t divided by 3t squared minus 1. And that is a function that will tell us our slope at any time. It doesn't tell us our slope at any ordered pair because we don't know the ordered pairs automatically. We can figure them out once we know the time, but we don't know the ordered pair automatically. It can help us answer questions like, when does our graph have a horizontal tangent line? Well, it would have a horizontal tangent line when this is equal to 0. And you only have to look at the numerator to know when that's equal to 0. So when negative 2t is equal to 0. So at t equals 0, we have a horizontal tangent line. That doesn't necessarily mean x is equal to 0, although it does for this particular parametric, because if I plug 0 in, I do get an x-coordinate of 0 and a y-coordinate of 4. So I will have a horizontal tangent line at 0, 4. I can also take a second derivative, and that's going to answer questions about concavity. So here's our first derivative. If I want to take a second derivative, I'm going to take the derivative of this with respect to time, because time is the independent variable in this equation. Take a deep breath, because we are doing quotient rule. and then some simplifying because it's too ugly to just leave it the way it is, unless this is a test and it's free response. Okay. Oh, I can do a little more simplifying. Now, um, it is tempting to call this your answer because you took a second derivative. You feel like you're done, but we took a second derivative with respect to t, and we want the second derivative with respect to x. So we need to take this thing that we have and divide it by dx dt. So we're going to divide that by 3t squared minus 1. And then just to kind of complete the pattern, we can simplify a little bit, multiply by the reciprocal, so we wind up with, and I want to point out that we asked a question earlier about where is the critical point. Well, at t equals 0, we have a critical point. One thing that the second derivative allows us to quickly answer is that a maximum, minimum, or neither at t equals 0? So let's go ahead and plug t equals 0 into that second derivative. We get 2 over negative 1 cubed. So it's negative, it's less than 0. So we have a horizontal tangent line at t equals 0, and we have concave down. So we have a maximum at t equals 0. Here's a picture of that parametric function. There's the path that the particle would take if it were traveling in the plane. There's the horizontal tangent line at t equals 0, which is at 0, 4, and it is concave. The curve is concave down at that point, so there is a maximum at t equals 0. Just a little more practice. We're going to take a second derivative here. I would recommend you pause and try it, and then unpause and take a look at my work. I'm not going to walk through every step. I'm just going to pause myself and write out my work, and so you should try it before you restart. Derivative is e to the t over 6t, and if I want to do a second derivative, if I want to do a second derivative of that, I have to take a derivative of this with respect to t and divide it by dx dt again. So I need to divide by 6t again. I've got quotient rule again, so it's going to be low d high minus high d low all over the square of what's below. So if I do a little bit of simplifying, I can get a 6 e to the t out of the numerator. And I have 6t cubed in the denominator. And I'm going to call that good. I could cancel 6 out, I suppose, but it's not really that big a deal. So that is my second derivative. And I could now figure out the concavity at any point. I'm actually going to not do this one because I'm going to have you